This video is about section 5.2 in our text on the definite integral. So in this section, we're going to expand on some of the ideas involving area that we saw in section 5.1. We'll also introduce some new terminology and notation. First of all, let's try to remember a little bit about what we did in section 5.1. Remember there that we were trying to approximate areas under curves using rectangles. And we saw that if we use a lot of skinny rectangles, we get a better approximation than if we just use a few thicker rectangles. That suggests that if we take a limit as the number of rectangles approaches infinity, then we should be able to get the actual signed area between the curve and the x-axis. Now you might remember that this signed area can be interpreted as distance traveled if the horizontal axis represents time and the vertical axis represents velocity. It's important to remember that the area formula that we developed in section 5.1, that is, taking the limit of a sum of rectangular areas, gives us not area but rather signed area. Remember, signed area is what happens when we count area above the x-axis, like A1 there, as being positive, and area below the x-axis as being negative. And the signed area then would be just taking A equaling A1 minus A2. Now these rectangular sums that we are computing in order to approximate these signed areas have a name. They're called Riemann sums, and this is named after the German mathematician Bernhard Riemann, who lived in the mid-1800s. We now introduce terminology and notation related to this process of finding the exact value of a signed area between a curve and the x-axis. The terminology in question is definite integral. So when you hear the words definite integral, you should be thinking about the process of finding the exact value of signed area. The process is this. We start with a function, which is defined on a closed interval, and we divide that interval up into n subintervals of equal width, delta x. So that should sound familiar from the previous video. So those delta x's give us the bases of our rectangles that we use to approximate signed area. And then to get the heights of each rectangle, we take each little base of rectangle and we pick a point within that base. And usually for convenience, we use the right endpoint of each little rectangular base. And we could also use the left endpoint or the midpoint or some other point like that. But the right endpoint typically is the most convenient. So then, once we know what our bases are, namely these delta x's, and once we know what our heights are, these f of x sub i's, then we can multiply f of x sub I times delta x to get the area of one of these little rectangles. And then to form the Riemann sum, that is this sum that approximates the signed area, we then just add up all of the little rectangles that add up the areas of the little rectangles we've created. Now what we said a little bit ago is that if we have more rectangles, then we get a better approximation. So to get the exact signed area, we take a limit as n goes to infinity of this sum that we've just created. And that should give us the exact signed area. So this object, this limit as n goes to infinity of this Riemann sum, is what's known as the definite integral of f from a to b. And instead of denoting it by this limit of this sum, we introduce this new notation here, featuring the elongated s, which is called an integral sign. And that notation actually makes some sense, right? Because the whole process involves adding or summation, and the elongated s is intended to indicate adding or summation. There's more terminology related to this definite integral notation. So here in the first bullet point, what you see here is notation for the definite integral of f from a to b. And remember that, if we compute this thing, gives us a signed area between the function and the x-axis on the interval from a to b. Now the number a is called the lower limit of integration. The number b is called the upper limit of integration. The function that's giving the heights of these rectangles is called the integrand, and the dx here that you see is called the differential. Now that thing you should be thinking of as just representing a very small delta x. So you can think of the differential, dx, as sort of representing the base of some very, very thin rectangle. And finally, we always want to keep in mind that this definite integral represents an exact signed area. It's not merely an approximation, it's an exact answer. We saw in the previous video from section 5.1 that computing the exact value of a signed area, that is, computing the definite integral of a function on a closed interval, can be a messy process involving a lot of sums and limits and other ugly-looking things. And we realized in the last video that there were some formulas involving summation that we needed to know in order to be able to compute these definite integrals. So the first formula here, which we saw in the previous video, just tells us how to quickly add all the numbers from 1 up to n. Right, if we want to add all those, the result is n times n plus 1 over 2. The second formula tells us how to add squares. And the third formula tells us how to add cubes, just as we saw in the previous video. And one other formula that should be here but is not is just what happens when you add up n ones, right? So that's just 1 plus 1 plus 1 n times, and so that should just be equal to n. So that's a formula that we also want to include in this list of formulas. Well, let's do a specific example now of a definite integral, where here we're going to use the limit definition of the definite integral to compute the value of this integral from 1 to 3 of 2 minus x dx. So we're going to let f of x denote 2 minus x in this computation. So we're told, according to our definition, that if we're going to do this integral, the integral of f of x dx, that is a limit as x goes to infinity of a sum, I equals 1 to n, of f of x sub I, delta x. So here the main thing to keep in mind for the moment is not the limit, but rather the sum. So what we're doing here, the delta x, remember, is the base of some little rectangle. The f of x sub I is the height of some little rectangle. Multiply those together to give the area of a little rectangle, and then we're just adding all of those up from I equals 1 to n to get an approximation. Now, in order to, turn this into a number, we need to be specific about what delta x is and about what x sub I is. So delta x, remember, is the length of each little sub-interval. And we get that by taking the length of our interval, which is 3 minus 1, and then dividing by the number of rectangles, which is n. So delta x is 2 over n. Now x sub I, on the other hand, how do we get it? Well, we start with our left endpoint, which is 1, and then we jump over I copies of delta x. So x sub I is 1 plus 2I over n, and delta x is 2 over n. So if we replace those things in our computation, so we're taking the limit now as n goes to infinity of this sum, I equals 1 to n, and we've got f of 1 plus 2I over n times 2 over n. Okay. And then what we need to do is just remember what f does. So f, remember, takes 2 minus whatever our input is. So it's 2 minus 1 plus 2I over n times 2 over n. And then once you make the computation of this stuff here that I'm going to write in square braces, once you simplify what's in here and then multiply through by 2 over n, what you should get is the limit as n goes to infinity of the sum I equals 1 to n of, let's see here, what is it? It should be 2 over n minus 4I over n squared. Okay. So now, ultimately, we're going to have to find a reasonable way to compute this sum, and then we'll have to compute the limit. So we're continuing with the example we started on the previous slide of computing the integral from 1 to 3 of 2 minus x dx, and we saw that that's the limit as n goes to infinity of this sum I equals 1 to n of 2 over n minus 4I over n squared. And now we have to turn that into a number somehow. And one thing we can do is simplify our lives by rewriting this as 2 over n times the sum, I equals 1 to n of 1 minus 4 over n squared times the sum, I equals 1 to n of I. Okay, all we're doing there is applying the distributive property and the commutative property of addition. So we're adding up all the 2 over n's first, we're adding up all the 4i over n squareds second, and then we notice that the first sum has a 2 over n in common in every term, so it can be factored out. The second term, the second sum of the 4i over n squareds has a 4 over n squared in common with every term, so it can be factored out. Okay, now once we're here, then those summation formulas that we talked about a few moments ago can be applied. So here we get 2 over n, and now in this sum we're just adding up n ones, which is the same as n. And then here in this second sum, we're adding up 1 plus 2 plus 3 up through n. And we saw that that result, according to the formula, was n times n plus 1 over 2. Now, when we take the limit of all this stuff, what's going to happen is that the first limit is 2. And this second limit is also 2. And so when we take 2 minus 2, lo and behold, we get 0. Now what does that tell us? Well, it tells us that this signed area between this function, 2 minus x, and the x-axis is equal to 0 on the interval from 1 to 3. And that ought to make some sense, because you could actually evaluate this integral just using geometric formulas, that is, like the areas of triangles. If you were to graph this function, say this is 1 and this is 3, what you would see is that the graph of 2 minus x actually looks something like this. And so if you look at the signed area under the curve, well, that portion of it that I'm drawing in is positive. This portion down here is negative, and when you add them together, what you wind up with is 0, just as we computed using this limit definition. So speaking of geometric methods, it turns out that there are some integrals, like the last one and this one that we're about to compute, where you can bypass the limit definition of the definite integral and just use geometric formulas to compute the corresponding signed area. So here, for this one, it's perhaps best to take this integral and rewrite it as this. So we'll integrate 1 first, and then we'll integrate uh, 2 times the root of 9 minus x squared second. So here, all we're doing in computing this, or splitting this up into pieces, is we're just saying that if we regard the integral as being just a type of sum, then we can handle the ones first and handle the 2 times 9 minus, or root 9 minus x squareds second. Okay, now each one of these separate integrals has a geometric picture. And so we're going to see what that geometric picture is. So for the first integral, we're over the interval from minus 3 to 0, and the 1 you can just regard as a constant function, 1. And then when we're computing this integral, we're asking ourselves, well, what is this signed area between the curve, the constant curve, 1, and the x-axis? Well, you get a rectangle of height 1 and of base 3, so the total area should be 3. Now for the second integral, we have this picture. So there's minus 3. Now root 9 minus x squared, that is a semicircle. So it looks like this. So it's what we have here is a circle of radius 3. And we're actually looking at just a fourth of that circle. So the area of that thing should be pi times 3 squared. That would be the area of the whole circle of radius 3. But then we're only taking a fourth of it, so we're going to divide by 4. So it's pi times 3 squared over 4. And so what we should get as a result is this first integral. The value of it is 3 because that's the area of that rectangle. And then we're going to take 2 times. So the 2 here is coming from that 2. And then we have the area of this quarter circle, which is pi times 9, which is 3 squared, divided by 4. And I guess if we wanted to get fancy here, we could factor out the 3, and we get a 1 plus pi over 2. So the total area is 3 times the quantity 1 plus pi over 2.